Welcome everyone. Today, we are diving into the core components of the central processing unit. Specifically, we will explore the three main parts that allow a computer to function: the control unit, the arithmetic and logic unit, and the registers. Let's look at how these three work together to process information. Let's start first with the control unit, also known as CU. Now, let's answer the question: what is the control unit? Think of the control unit, or CU, as the manager or coordinator of the CPU. Its job is to manage and coordinate every operation that happens inside the processor. It is located right inside the CPU as one of its three main pillars. A key point to remember, and this is a very important characteristic, is that the control unit does not process data itself. Does not process data itself. Instead, it acts like a conductor in an orchestra. It directs and manages the other components to make sure they do their job at exactly the right time. Moving on to the main functions of the control units. 1. The control unit controls the order of instructions. It ensures that every task runs in the correct sequence. Without this oversight, the processing would be chaotic and inefficient. 2. It acts as the manager for other CPU components, specifically the ALU and the registers. The control unit coordinates when the ALU should perform a calculation and directs the registers on exactly when to store or retrieve data. It uses the internal CPU buses as communication lines to send these directions. Thirdly, it is responsible for fetching instructions. It reaches out to the RAM or main memory to retrieve the next instruction and brings it into the CPU to be prepared for action. Continuing with the main functions of the control unit, we move into how it actually prepares and executes tasks. The fourth function is decoding instructions. Once an instruction is fetched, the control unit interprets it to understand exactly what needs to happen. It determines the specific operation required and identifies which pieces of data are needed to get the job done. Fifth, it fetches the required data. Just as it fetched the instructions earlier, it now retrieves the specific data from the RAM and brings it into the CPU for immediate use. Next, it sends data and those instructions to the ALU. It sends that data and those instructions to the ALU. Here, the control unit acts as a director telling the arithmetic and logic unit exactly which calculation to perform and providing it with the necessary information to do so. Finally, the control unit handles the output. Once the processing is complete, it sends the results to the correct destination, whether that means storing the data back in memory or sending it out to your screen or other output devices. Now that we know what the control unit does, let's look at how it communicates with the rest of the system. First, it uses the internal CPU buses, which act like the CPU's internal highway system. The address bus is used to send specific locations in memory. The data bus is what actually carries the information back and forth. And the control bus carries the specific command from the control unit. Speaking of commands, the control unit sends control signals to tell the computer exactly what to do. For example, it sends a read signal to retrieve data or a write signal to store it. It also sends execute signals to start an operation and timing signals to keep everything in synchrony. Finally, it coordinates timing by working closely with the CPU clock. This ensures that every operation happens in the exact correct order. By synchronizing all the components, the control unit prevents data from crashing into each other and ensures the processor runs smoothly. Now let's bring everything together and look at the control unit's role in instruction execution. This is a step-by-step process that happens millions of times every second. In step 1, we fetch. The control unit sends a memory address through the address bus and a read signal through the control bus. The instruction then travels from the RAM into the CPU via the data bus. In step 2, we decode. Once the instruction is inside, the control unit interprets it. It figures out exactly what operation is needed and identifies which specific data is required to complete the task. In step 3, we fetch the data. If the instruction needs extra information to work, the control unit goes back to the memory to retrieve that data and brings it into the CPU registers. Step 4 is the execution phase. The control unit sends the instruction and the data to the ALU. It directs the ALU on exactly which calculation or logic operation to perform. Finally, in step 5, we output results. The control unit takes the finished work from the ALU and send it to its final destination, whether that is storing it back in memory or sending it to an output device like your monitor. This completes the cycle and the control unit immediately starts again with the next instruction. To help visualize how the control unit works, let's look at a few real-life analogies. These examples mirror exactly how the CPU functions within a computer. First, think of the control unit as a traffic officer. A traffic officer at a busy intersection. The officer doesn't drive the cars, but they direct the flow of traffic, telling vehicles when to stop, go, or turn. This prevents collisions and keeps everything moving smoothly. Similarly, the control unit directs the flow of data within the CPU to prevent errors and chaos. Second, we can compare it to an orchestra conductor. A conductor doesn't play every instrument. Instead, they coordinate all the musicians, telling them exactly when to play to ensure perfect harmony and timing. This is just like the CU synchronizing every component of the CPU to work together at the right moment. Finally, consider the role of a school headmaster. The headmaster manages the entire school's operations and directs both teachers and students to ensure the day runs smoothly. Crucially, the headmaster doesn't usually teach the classes directly. In the same way, the control unit manages all CPU operations, but as we mentioned earlier, it does not process data itself. It does not process data itself. It simply ensures that the components that do process the data are doing their jobs correctly. To truly understand the importance of the control unit, we have to ask, what would happen if it stopped working? Simply put, the entire system would collapse. Without the CU, there's no coordination. Instructions would lose their sequence, leading to random and chaotic processing. The internal components of the CPU would lose their ability to communicate. The ALU will never receive its instructions, and the registers would have no idea when to store or retrieve data. This means the fetch, decode, execute cycle, the heartbeat of the computer would fail completely. No programs could run, and the computer would cease to function. It would be a total system failure. Think of it like a human body without a brain to send signals to the limbs. Or going back to our traffic light analogy, it would be like a major city with no traffic lights or signals. You would have immediate chaos and gridlock, and nothing would move. This highlights why the control unit is often called the brain within the brain of the computer. The brain within the brain of the computer. To wrap up our discussion on the control unit, let's review the key points. Remember, the CU is the manager of the CPU, manager of the CPU. It does not process data itself, but it is responsible for the order of every instruction and the coordination of all components, including the ALU and the registers. It keeps everything connected using the internal buses. We also looked at the 7 main functions that define its role. 1. It controls the instruction order. 2. It manages other components. 3. It fetches instructions from memory. 4. It decodes those instructions. 5. It fetches the required data. 6. It sends everything to the ALU for processing. 7. It handles the output of the results. In short, the control unit is essential for organized processing. Without it, the CPU cannot function and the computer cannot run. It is the director that turns a collection of parts into a powerful processing machine. Now let's look at the arithmetic and logic unit, ALU. Now that we understand the manager, let's look at the worker. What exactly is the ALU? The arithmetic and logic unit, or ALU, is the part of the CPU responsible for all calculations and logical operations. Just like the control unit, it is located right inside the CPU as one of its 3 core components. If the control unit is the manager, the ALU is the calculator and the decision maker. A key characteristic to remember is that the ALU is where the actual data processing happens. While other parts move or store data, the ALU is the component that actually changes it by performing maths and making logical decisions. The ALU handles 2 main types of operations that allow a computer to function. The first type is arithmetic operations. This is where the CPU manipulates numbers and performs mathematical calculations. Think of this as the computer's internal calculator. It handles everything from simple addition and subtraction to more complex multiplication and division. The second type is logical operations. This is the decision-making function of the CPU. Here, the ALU uses Boolean logic to compare data. It asks questions like, is this value equal to that one? Or is this number greater than the other? By using logical gates like AND, OR, and NOT, the ALU can make the complex decisions required to run software. In short, arithmetic is how the computer calculates, and logic is how the computer decides. Let's take a closer look at arithmetic operations. At its most basic level, the ALU is designed to perform 4 fundamental tasks. First, we have addition. This is used for everything from calculating a high score in a game to summing up values in a spreadsheet. Next is subtraction, which the computer uses to find differences or determine remaining amounts of data. Then we have multiplication, used for tasks like calculating screen areas or repeated additions. And division, which is essential for sharing data equally or finding averages. It's important to remember that every complex mathematical calculation in a computer program, no matter how advanced it looks on screen, is actually broken down into these four basic operations by the ALU. Beyond basic maths, the ALU is responsible for comparison operations. This is how the computer evaluates data to make decisions. It essentially asks 6 types of questions that result in a simple true or false answer. First, it checks for equality. It asks, is value A equal to value B? If it's looking for the opposite, it uses not equal to. This is fundamental for tasks like checking if a password is correct. Next, the ALU performs size comparisons using less than and greater than. For example, it might ask if a file size is less than the available storage space. Finally, it handles more inclusive comparisons, less than or equal to, and greater than or equal to. These are vital for setting limits, such as checking if a user has reached the maximum number of login attempts. By using these 6 comparisons, the ALU provides the logic needed for the computer to react differently depending on the data it receives. Now that we know what the ALU does, let's look at how it actually works within the system flow. This process happens in 4 clear steps. Step 1 is the handover. The ALU receives data it needs from the registers, where it has been temporarily stored for quick access. Step 2 is receiving the instructions. The control unit acts as the supervisor here, sending control signals to tell the ALU exactly which operation it needs to perform on that data. Step 3, the ALU performs the operation. Whether it's an arithmetic task like addition or a logical comparison, this is the moment where the actual work happens. Finally, in step 4, it sends the results back. Once the calculation or decision is complete, the processed information is stored back in the registers. From there, it can be sent to the main memory or an output device like your screen. An important takeaway here is that the ALU never acts alone. It works under the direction of the control unit at all times, creating a seamless partnership within the CPU. To see the ALU in action, let's look at some real-life examples of how it handles our daily tasks. First, imagine you are playing a video game. Every time you pick up an item or defeat an enemy, the ALU performs an arithmetic operation. It adds those new points to your current score. For example, taking 50, 30, and 20 to give you a total of 100 points. Second, Consider the simple act of logging in. When you enter a password, the ALU performs a comparison operation. It asks, is the password just entered equal to the password stored in the system? If the ALU finds this is true, you are granted access. If it is false, you are denied. Finally, think about online shopping. When you click buy, the computer needs to know if you have enough balance. The ALU uses a greater than or equal to comparison to check if your available money is greater than or equal to the item price. As you can see, whether it's for entertainment, security, or commerce, the ALU is the engine making these essential decisions for us every second. At this point, we can see the vital partnership between the control unit and the arithmetic and logic unit. They function as a highly coordinated team. The control unit's role is to act as the supervisor. It sends the specific instructions to the ALU, telling it exactly which operation to perform. It also provides the critical timing signals that coordinate the flow of data, ensuring everything happens at the right millisecond. The ALU's role, on the other hand, is to be the engine. It receives those instructions and performs the actual calculations or comparisons. Once the work is done, it sends the results back and waits for the next instructions to arrive. A perfect analogy for this is a manager and a worker. The manager here is a control unit. It gives the instructions and oversees the schedule. The worker, here the ALU, performs the actual task and reports back the results. Without the manager, the worker wouldn't know what to do, and without the worker, the manager's plans would never be completed. This partnership is what makes computer processing possible. To make it simple, you can think of the ALU as a calculator with a brain. First, let's look at that calculator function. This represents the arithmetic side of the unit. It can perform mathematical operations like addition, subtraction, multiplication, and division at incredible speeds. If it involves numbers, this internal calculator handles it. Next is the brain function, which represents logic. This is what allows a computer to do more than just maths. It allows it to make decisions by comparing values and determining if a situation is true or false. The ALU provides the logical reasoning required to run your software. However, there is one key thing to remember. The ALU always follows instructions. Just like a handheld calculator sits idle until someone presses the buttons, the ALU cannot work independently. It relies entirely on the control unit to give it instructions and tell it exactly what to do next. Now, to summarize our look at the arithmetic and logic unit, let's review the essential points. The ALU is the calculator and decision maker of the computer, located inside the CPU. It is the specific place where the actual data processing happens. We've seen that it handles two distinct types of operations. First, there are arithmetic operations, covering your basic math like addition and subtraction. Second, There are logical operations, which include Boolean logic and all comparisons like greater than or equal to, that allow a computer to make decisions. In terms of workflow, the ALU follows a specific cycle. It receives data from the registers, takes its instruction from the control unit, performs the required operation, and sends the result back to the registers. The most important thing to remember is that the ALU is a specialist that works under the direction of the control unit. It is the engine that makes all data processing tasks possible, turning raw data into meaningful results. Now let's look at registers. Now let's move to our third core component. What are registers? Registers are temporary storage areas located directly inside the CPU. They hold the specific data, instructions, and memory addresses that are being processed at this very moment. You can think of them as the CPU's immediate workspace. While their location is internal, their size is actually very small, usually measured in just bytes. However, don't let the size fool you. Because of their location, registers are the fastest type of storage in the entire computer. They are much faster than your RAM or your hard drive. The main purpose of a register is to provide the CPU with immediate access to information by keeping the most important data right where the processing happens. Registers ensure the CPU doesn't have to wait for information to travel from slower parts of the system. So why are registers so special? It comes down to three main factors: speed, capacity, and location. First, as we've mentioned, they are the fastest type of storage in existence. Because they are located directly inside the CPU, there is virtually zero travel time for data. This allows for immediate access and ensures there's no delay during high-speed processing. Second, they have the smallest capacity. Unlike your hard drive, registers are not meant for long-term storage. They typically hold only a few bytes, just enough to store the specific data that is being processed at this exact microsecond. Third, their location inside the CPU is a major advantage. Being part of the CPU architecture means they have a direct high-speed connection to the ALU and the control unit, requiring no external communication. To put this into perspective, let's look at the speed comparison. In the world of computing, registers are the undisputed champion of speed, followed by cache memory, then RAM, and finally our hard drive or SSD. While a hard drive holds the most data, the registers are what allows the computer to actually think at the speed of light. Now let's look at the purpose of registers. While they are small, They are essential for keeping the CPU running efficiently. They serve four main purposes. First, they temporarily store data being processed. This includes the specific numbers or information the ALU is working on right now, as well as any intermediate results from a long calculation that aren't quite finished yet. Second, they store program instructions. A register holds the specific command currently being executed, while another keeps track of exactly where the next instruction is located, so the CPU never loses its place. Third, they store memory address. Registers act like a GPS for the CPU, holding the specific addresses or locations in the RAM where the next pieces of data or instructions can be found. Ultimately, all of this serves to enable fast CPU operations. By having everything right at its fingertips, the CPU eliminates the waiting time for data and can work at its maximum possible speed. It is important to note that different registers perform different functions. Each one has a specific role to play in this high-speed process. Now let's look at the first of our specific registers, the memory address register, or MAR. The primary function of the MAR is to store the specific address in memory that is currently being read from or written to. Think of it as the CPU's way of pointing at a specific location. To understand how it works, imagine the CPU needs data from memory location 5000. The MAR will store the value 5000 and send it to the RAM via the address bus. This tells the RAM exactly which shelf or location to look at. A simple analogy for this is a house address. If you want to visit a friend, you need their specific house number to find them. The MAR holds that house number for data in the memory, telling the computer exactly where to find or store information. For example, if the CPU needs to read data from location 8000, the MAR stores that number. The address bus then carries it to the RAM, which immediately knows how to retrieve the data from that exact spot. Without the MAR, the CPU would have no way of knowing where any of its data is kept. Next, let's look at the program counter, commonly referred to as the PC. The function of the PC is to store the memory address of the next instruction to be executed. While the CPU is busy working on one, the PC is already looking ahead to the next one. To understand how it works, imagine the current instruction is at memory location 2000. The PC or program counter will store 2001. As soon as the current instruction finishes, the program counter or PC tells the CPU exactly where to go next. A key feature here is that the PC or program counter automatically increments or increases after each instruction is fetched, ensuring the program stays in the correct order. A great analogy for the PC is a bookmark in a book. Just as a bookmark keeps track of exactly where you are so you can pick up where you left off, the PC keeps track of where the CPU is in a program. It ensures the computer never skips a line or loses its place. For example, if an instruction at location 3000 is currently executing, the PC or program counter is already holding 3001. Once that task is done, the CPU fetches the next instruction from that 3001 address, and the PC or program counter immediately updates to 3002. This constant updating is what allows a computer to run a long sequence of instructions without stopping. Now let's look at memory data register, or MDR. While the MAR, which we discussed earlier, holds the address of the data, the MDR holds the actual data itself as it is being transferred to and from the processor. How it works is quite simple. It acts as a temporary holding area. When the CPU reads from memory, the data sits in the MDR before it is processed. Conversely, when the CPU writes to memory, the data is placed in the MDR first before being sent out to the RAM. A perfect analogy for the MDR is a delivery box. A delivery box is a temporary container that carries items between two locations. Similarly, the MDR carries data between the CPU and the memory, acting as the secure holding place during the transfer. Let's look at two examples. First, when reading from memory, if the CPU requests data from location 5000, that data is retrieved from RAM and stored temporarily in the MDR. From there, it is moved to the ALU or other registers for processing. Secondly, when writing to memory, once the CPU has finished processing a piece of data, it places that results into the MDR or memory data register. The data is then sent across the bus to the RAM for long-term storage. The MDR ensures that data is always ready and available exactly when the CPU needs it. Now that we've met the individual players, let's see how the registers work together in a perfectly synchronized process. This cycle happens millions of times every single second within your computer. In step 1, the program counter kicks things off by providing the address of the very next instruction. In step 2 and 3, the memory address register receives that address and sends it out to the RAM via the address bus. It's essentially telling the memory, I need the information located right here. By step 4 and 5, the instruction or data is fetched from the RAM. It travels back and is caught by the memory data register, which acts as our temporary holding area. In step 6, that data is moved to where the work happens, either the ALU for calculation or the control unit for decoding. Step 7 sees the results of that work stored back into the registers for immediate use. Finally, in step 8, the program counter increments, moving to the next address, and the entire cycle repeats instantly. This seamless handoff between registers is what allows your computer to execute complex software with incredible speed and precision. To fully understand the role of registers, it helps to compare them to RAM. While they both store data, they serve very different purposes in the hierarchy of your computer. As a general rule, registers are for data being processed right now, whereas RAM is for data that might be needed soon. When we look at the location, registers are right inside the CPU, while RAM sits further away on the motherboard. This proximity leads to a massive difference in speed. Registers provide immediate access, while RAM, though fast, is significantly slower by comparison. In terms of capacity, RAM can hold gigabytes of data, whereas registers are incredibly small, holding only a few bytes. There is also a difference in cost. Byte for byte, registers are the most expensive type of memory in your system. However, both are volatile, meaning they both lose their data when the power is turned off. In summary, the CPU uses RAM as a large warehouse for everything it might need during a session, but it uses registers as its personal desktop to hold only the specific tools it is using at this exact microsecond. Now let's look at the bottom line. How do registers actually speed up processing? The primary benefit is that data is immediately available. Because the information is right there inside the CPU, there's no waiting time. This allows the processor to work continuously without pause. By eliminating the travel time from slower memory, we remove processing delays and bottlenecks, allowing the CPU to operate at its absolute maximum speed. To visualize this, think of the workbench analogy. If you are a carpenter, having your tools right on your workbench is like having data in registers. You can reach out and grab what you need instantly. However, if your tools are in a storeroom or storage room, which represents your RAM, you have to stop what you are doing and walk to get them every single time. That walking back and forth is what slows a computer down. The performance impact is massive. Without registers, the CPU will spend most of its time sitting idle, waiting for data to arrive from the RAM. With registers, the CPU can process data the moment it is ready. The result is dramatically fast, responsive performance we expect from our devices today. To bring our discussion on registers to a close, let's recap the essential points. Registers are the fastest and smallest storage areas in the entire computer. Because they are located directly inside the CPU, they provide the essential temporary workspace for any data or instructions that are being processed at this very moment. We focus on three main types of registers that keep the system moving. The MAR, which stores the specific memory address the CPU needs to find. 2. The program counter, or PC, which looks ahead to store the address of the very next instruction. 3. The MDR, which acts as the holding area for the actual data being transferred. Each of these has a specialized role. The MAR knows where to find data. The PC knows which instruction is next. And the MDR acts as a temporary holding or holder for the data itself. Ultimately, registers are essential for fast CPU processing. By working in perfect harmony with the control unit and the ALU, they provide immediate data access and eliminate the waiting time that would otherwise slow our system down. This concludes our look at the internal architecture of the CPU. Thank you. Let's start first with the control unit, also known as CU.